This is Chapter 9, Sections 9.1 and 9.2. This is all about the shapes, geometric shapes of molecules. This is not going to be an easy part of the chapter, so let's dig into it. We got 5 basic shapes, and it's going to be an interesting story as to see how they all fit together. So let's continue on. There we go. So molecular shapes. So take a look at, we have 2 molecular shapes here. You see that you have CO2 and SO2. And you would think that they would look the same because it's something bonded to oxygen, and the difference between C and S is not that big a difference. They're both nonmetals. The only difference is the number of valence electrons they have. But notice the shapes are different though. Why are the shapes different? If we have the same formula, same kind of formula with very similar, like the C and the S are both very similar as far as electronegativity. The only difference is the number of bonds that carbon forms is 4, and the typical number of bonds that sulfur forms is 2. So you can see that there's a difference between the 2 of them though. So take a look. This is AB2, AB2. So AB2 would also be like NO2 or any of these others that would, I'm trying to think if there's anything else we could do. I guess we could do like a BE2 or maybe an SRH2 or something like that. So anyway, my point is that we have specific shapes. Notice how even though these 2 compounds look like they should be similar, notice that one's linear and one's bent. What does linear and bent mean? Well, we're going to get to that. By noting the number of bonds and non-bonding electron pairs, we can easily predict the shape of the molecules. Easily. That's what we're going to get into. So what determines the shape of the molecule? So here's the deal. You have 2 different types of electron pairs when we write a Lewis structure. You have bonding pairs, which you see here in red, between the nitrogen and the hydrogen, and we have non-bonding pairs, or what we call lone pairs, that I just put in green there. They both determine the shape. As a matter of fact, each one of these, whether it's bonding or non-bonding pairs, push off on each other, they repel each other, and they determine the shape of the molecule. Now the difference is that whatever it is, whether it's bonding, like you see here, for the green, bonding, or non-bonding with the red, I mixed it up this time, it doesn't matter. We count the number of electron domains. So we count 1, 2, 3, 4. So if we have 4 electron domains and they all push off on each other, then we have the same. Any molecule that has 4 electron domains, like this one here has 4 electron domains, and there's 1A and 3B. Or you could have 1A and 4B. Like they can all be the same shape as long as you have 4 electron domains. Electron domain is anything that is bonding and non-bonding. And it doesn't, like one double bond is a single electron domain. So that's how we count electron domains. Electron domains is a fancy way to say any place where there's electrons outside the central atom, or like attached to the central atom. That's what it matters. So that's how we determine it. So there's something called the valence shell electron pair repulsion theory, also known as VSEPR. So what is VSEPR? VSEPR is the way that we describe how a molecule gets its shape from the electrons that are bonded or on, like bonding or non-bonding for the central atom. Okay, that's what VSEPR does. We imagine, I've said this before in class, imagine having balloons, and you want to tie the knots of those balloons together. What if you have 3 balloons? Well, if you have 3 balloons, you would have one balloon tied here to another balloon tied there, and another balloon tied there. And you would start to see what that shape looks like. Well, molecules work exactly the same way, but instead of balloons, we have electrons. So what are the shapes? Okay, these 5 shapes I want you guys to know. I really do. Just like I want you to know them better than the polyatomic ions you refuse to learn. So the shapes are very simple. If we have AB2, AB2 is linear, AB3 is trigonal planar. Trigonal meaning triangle, meaning 3 parts, and planar, meaning all in the same plane. Honestly, that's what it means. The next one is the most common. This is tetrahedral. This is when you AB4, and the 4 means 4 electron domains. AB5 is trigonal bipyramidal. Pyramidal meaning like, well, trigonal first of all meaning a triangle, and bipyramidal meaning 2 pyramids separated like by base on base. So you have a pyramid on top and a pyramid on the bottom. That's what bipyramidal means. So trigonal means a triangle pyramid, bipyramidal means 2 pyramids attached by the bases. And then octahedral is another way to say like an 8-sided die. I don't know if you've ever seen an 8-sided die, but like this, and it's got, basically it's a square pyramid, but it's 2 of them, so it would be square pyramidal, bipyramidal, but we just call it octahedral. And because there are 6 parts of this, 6 things on here, you could call it hexahedral, and I would definitely accept that as a good description of the. So octahedral or hexahedral because of the 6 things that we have. So this is AB5 for trigonal bipyramidal, and AB6 for octahedral or hexahedral. So these are the electron domain geometries for 2 through 6 electron domains around the central atom. We don't go higher than 6 because no central atom bonds to more than 6 things at one time. 6 is the upper limit, and 2, if you have just one thing bonded, like the compound CO, then obviously it's the same as linear, like it's, you know what I mean, it doesn't matter. Okay, so electron domain geometries. So all one must do is count the number of electron domains. So here, for this Lewis structure for NH3, so NH3 is my formula. The NH3 doesn't tell me what structure it's going to have. I have to literally draw the Lewis structure and count 1, 2, 3, 4. I include the non-bonding pair. That's there. And that gives us 4 things that would be like an AB4, and that would be tetrahedral. And that's how you do it. So our base shape is tetrahedral. Now, tetrahedral with 1 non-bonding pair gives us a different shape. It's not tetrahedral. The base shape is tetrahedral, but now the molecule looks like, and here I'll show you, trigonal pyramidal is what we call that. And there's a whole list of stuff. So the Lewis structure here tells us how many electron domains we have. I count the number of electron domains, and it gives us the tetrahedrals, our base shape. That is our electron domain geometry. That's a big fancy way to say that we're counting all electrons like that, and that's 4, and that's tetrahedral. And then with 1 non-bonding pair, that's why I did a double circle around it. The 1 non-bonding pair, this non-bonding pair up here doesn't show up in the molecular geometry. So this is trigonal pyramidal. That's tetrahedral with 1 lone pair, or 1 non-bonding pair. So the electron domain geometry is often not the shape of the molecule. So if you have a non-bonding pair, or 2, or 3, then your shape of the molecule is going to look different than your electron domain geometry does. So the molecular geometry is that defined by the position of only the atoms in the molecules, not the non-bonding pairs. So we don't see the non-bonding pairs up above, and that's why I just erased them to prove that point. So within each of the electron domains, then there might be more than 1 molecular geometry. Okay, so that means that if we have something like CH4 here, CH4, all 4 of these bonds are bonding electrons, and that would then our shape, I'm not sure why I can't spit this out, but our shape is tetrahedral. Our molecular geometry would be tetrahedral also. So this is a case when there's no non-bonding pairs that the electron domain shape and our molecular shape are equal to each other. They're the same then, when there's no non-bonding pairs. When there's 1 non-bonding pair, that changes the shape. So here we have a shape called trigonal pyramidal because we got rid of one of these bonds and replaced it with a non-bonding pair. So what happens if I have 2 non-bonding pairs on the same shape of tetrahedral? Then we get what's called bent. Very scientific, isn't it? That's what H2O looks like, though. That's why we always draw oxygen and hydrogen in water to look like this, and never do we draw it to look like this, because it doesn't look like that. Okay, it looks more like this, where we have non-bonding pairs like that. Okay, so this helps us figure out what the shapes of the molecules actually are, but we don't actually see the non-bonding pairs. All we see are the hydrogens at a weird angle. So there's a part of the book that has all of this, the whole charts for, let's see, linear, trigonal, pyramidal, and trigonal planar, linear, trigonal, planar, so 2, 3, and 4, and tetrahedral. And then it gets on to the other ones. There's trigonal planar. So what happens if we have 3 bonding domains, or 3 electron domains, and no non-bonding domain? That's called trigonal planar. What if we have 1, 2, and 1, 2 bonds and 1 non-bonding? Then it's called bent. Okay. We go through this. Non-bonding pairs and bond angles. So there's something you should know. Non-bonding pairs of electrons actually take up more physical space. Notice the 2 pictures that you see here. Here is one where this may be like hydrogen and hydrogen, and then we have the 2 electrons in here, but because the 2 electrons are being stretched between the 2 hydrogens, it kind of narrows what the area for the bonding area in between the 2 hydrogen looks like. However, down here we have oxygen. I have pair of non-bonding on that side. This would be the pair of non-bonding on this side. Notice it's much wider, so it takes up more room. So normally, when we have something like a tetrahedral, where it looks like this, and then they do this to show that it's out in front, and they do this to show that it's back behind, like this. Each one of these angles here is 109.5 degrees. Okay, but if you have 2 non-bonding pairs, then it shortens that angle down between the 2 bonds that are actually happening there to 104.5. We take away 4 degrees of angle. So if there's only 1, it's 107. Only 1 non-bonding pair. If there's 2 non-bonding pairs, it's 104.5. And if there are no non-bonding pairs and they're all bonds and they all take up the same room, it's 109.5. So we keep going. Yes, I'm going to ask you to know the bond angles. It's not that tough. Your choices are literally 90, 180, right? Or 120 when we have trigonal planar, and 109.5 when we have tetrahedral. That's all you have to remember. And then I'll show you which ones go. I'm going to cut here because we are absolutely getting long for this screencast.